Okay. Hey, everyone. Well, we've talked about how stars are born. We've talked about how they live their lives as main sequence stars. And now it's time to talk about what happens as they die. So, when that when that star runs out of hydrogen in the core, then the core is pure helium. And there's still some simmering right above that, right? The core is helium. There's that layer right above the core that is over 10 million Kelvin. And so it's going to be fusing hydrogen into helium right above it. And that's going to be building up more of that helium ash onto the core. And that means that the core is getting more massive. And if the core is getting more massive, then its gravity is stronger. And that's going to cause it to contract. It's going to shrink. And what happens to a gas when you compress it? It heats up. So there's heat coming off of that collapsing helium core. And there's heat coming off of the layer of hydrogen burning into helium right above that, and all of that heat is working its way out from the core out to the outer atmosphere of that star. And so the outer envelope of the star is still mostly hydrogen, and that hydrogen is being heated up from inside. It drives that hydrogen to convect. And all of that is creating extra radiation pressure until the radiation pressure on the surface is stronger than the gravitational pull of the surface, and that causes the star to expand. And so the core, this is where, as the stars die, things get more complicated, because while the star was a main sequence star, hydrostatic equilibrium was maintained everywhere in the star, in the core and in the envelope. Here's where that stops, right? Because in the core, gravity is winning and pressure is losing, and the core is shrinking and heating up. In the outer envelope, pressure is stronger than gravity, and that causes the star to expand and become a giant. But then what happens to a gas when you let it expand? When you let this envelope gas expand, it's going to cool off. And so if it's getting cooler, then the star is getting redder, which is why those stars are called red giants. Because they're red and they're giant. It's right there in the name, right? All right. Eventually, that collapsing helium core gets smaller and smaller and denser and hotter until it gets heated up to over 100 million Kelvin. And 100 million Kelvin is the magic number for fusing helium into carbon. And that's where the star gets a second lease on life, right? That star has found a new power source for a little while, right? It is now fusing helium in the core into carbon, and that reestablishes some hydrostatic equilibrium. The helium burning into carbon in the core is producing radiation pressure, and also there's that layer of hydrogen burning into helium right above that, also making some radiation pressure, and this new radiation pressure brings gravity back into balance, and things slow down. Things take a pause for a minute. For as long as that core can be burning helium into carbon and burning hydrogen into helium, right? The outer envelope is out here, and this new radiation pressure comes and balances with gravity again, right? Gravity's always pulling in, that radiation pressure is pushing out, and so the surface of that star stops expanding, and it's going to shrink down a little bit. It's going to shrink down a little bit as things settle down, the convection slows down, and it's going to get a little smaller. It's not becoming a main sequence star again, right? It's a horizontal branch star, but it is not a horizontal branch star that is actively expanding like it was as a red giant, right? It has come back into balance, pressure pushing out, gravity pulling in. That causes that surface to stop expanding and shrink down a little bit. And if the gas shrinks down, then it's going to heat up, and it's going to heat back up to being sort of yellow hot, right? It's not a red giant anymore. It's kind of a yellow giant. Or, that's the horizontal branch. Eventually, though, the core runs out of helium. The core is now a purely carbon core. And again, once the nuclear reactions in the core stop, there's no more new radiation pressure happening there, and it starts shrinking down again and heating up again and releasing a whole bunch of heat out into the outer envelope, and the outer envelope is being heated from underneath, and it expands again, and it climbs back up the red giant branch, right? It goes back to getting bigger, it goes back to getting cooler, it climbs back up the red giant branch as the surface expands and cools off. It becomes what's called it becomes an asymptotic red giant, right? Asymptotic kind of means that it's approaching. It's getting close to being a supergiant, but it's never going to quite be a supergiant, because before it can expand and cool off and become a red supergiant, the outer layers of the star will blow away, right? There's so much heat being released from the carbon core and from the layer of helium burning on top of that and the layer of hydrogen burning on top of that. And all of those layers are releasing all of this heat all at once. And all that heat creates all this extra radiation pressure that causes the outer layers of that star's envelope to expand and keep on expanding and eventually blow away. Right? That's how low mass stars end their lives, right? Blowing out their outer atmosphere out into space as the planetary nebula. And once all the outer layers are blown away, all that's left is the core. And what that core becomes then is the white dwarf, right? Every white dwarf star in the universe is just the leftover core of a low mass star after all the outer layers have blown away. Right. And that's for a low mass star, right? For stars that are born with masses less than 8 solar masses. If your star is born with more than 8 solar masses, then that carbon core shrinks down even more. Gravity is so strong. If that star is born with more than 8 solar masses, then the star's got more mass, gravity is stronger, eventually that carbon core just collapses under its own weight, and it shrinks down and becomes the neutron star. Or a black hole. If it's even more massive, it becomes a black hole. And as that carbon core collapses down and becomes the neutron star or the black hole, that creates that flash of neutrinos, and it's the neutrinos flashing out of the core, hitting all these other layers that blast all the other layers of the star away as your supernova explosion. Right? So, high mass stars end their lives as a powerful supernova. I'll just say SN for short. Right? The outer layers explode, and all that's left at the very end, after the supernova has blown away, is the core, and the core is either a neutron star or a black hole. Mass is destiny, right? Because the mass that a star is born with determines how strong gravity is going to be, especially in the core, and how strong gravity is determines what happens to the core at the end. If a star is born with less than 8 solar masses, the core will collapse down into the white dwarf. If the star has more than 8 solar masses, if it has between 8 and 20 solar masses, then that carbon core will collapse down and become the neutron star. If it's more than 20 if the star is born with more than 20 solar masses, then it'll collapse down even more. It'll collapse down completely and become a black hole. Either way, when the star collapses into the neutron star or whether the core collapses into the black hole, both of those processes create that flash of neutrinos that slam into the outer layers of the star's atmosphere and blast the whole thing away as the supernova. That's why mass is destiny, is because the mass of the star determines gravity, and the strength of its gravity determines what happens from there on out. This is why the hydrostatic equilibrium and radiation pressure is so important, because we've been talking about nuclear reactions and the radiation pressure pushing outwards on gravity. The one thing that is just a constant in that star is gravity. Gravity is constantly trying to collapse the whole star down, and hydrogen fusion, helium fusion, all of that collapse that creates the radiation pressure, all of that, the life of a star is all about fighting against gravity. And once that star has run out of fuel, the radiation pressure loses. Finally, at long last, gravity wins, and the life of that star ends. Okay. So if we start with a low-mass star like the Sun, a G-type star, right? That star starts out, if it's a G-type star, that star is born as a main sequence star. So, A, right? And then it climbs up the red giant branch to B. And then once the helium ignites, it's going to settle onto the horizontal branch. Right? There's your horizontal branch while it's burning hydrogen into carbon. Once the hydrogen has fully converted into carbon in the core, then the star climbs back up the red giant branch to become an asymptotic giant. And like I said, it's approaching the supergiant phase, but it's never going to reach it. Right? Because once the carbon core collapses down, the rest of the star blows away, and all you're left with is your white dwarf. Right? The star kind of goes from D, and then the outer layers blow away, and all that's left at the end is the hot, contracted carbon core, and that's what your white dwarf is. What event does the low-mass star die as? It dies as the planetary nebula. High-mass stars, by contrast, right? They are, if we start as an A-type star, right, then you're starting here on the main sequence. Then once the hydrogen runs out, then it approaches and becomes, becomes a supergiant. A red supergiant. And then the carbon ignites, and it kind of goes through its own little... These high-mass stars kind of go through their own horizontal branch phase, where it'll go from A to B... I'm gonna... Because when the star turns from a main sequence into a supergiant, it kind of just... It maintains that... It maintains the same luminosity... And so it's more of a like that, right? It goes from here, becomes the supergiant, and then it can kind of like wander over just a little bit, still a supergiant, but it'll wander over here to its own little horizontal branch phase, and then it'll wander back again, and so it doesn't just go to B and then stay there. It can kind of go to B as like a red supergiant and then a yellow supergiant when it starts burning helium. And then back over here to the red end of the supergiant phase. At which point, boom, the whole thing blows up as the supernova. and then it becomes either the neutron star or the black hole, right? Where do you plot a neutron star or a black hole on an HR diagram? Well, you really don't, because neutron stars are very low luminosity, but they're also very hot, right? So you've got main sequence stars, red giants, supergiants, white dwarfs. You don't really put the neutron stars on an HR diagram because they're really hot but really small, and therefore, because they're really hot but really small, they're also very low luminosity. So where would you plot that? I mean, you could plot it over here. So you don't. You just don't, right? Because if you put a neutron star on an HR diagram, like say, like, okay, we'll put the neutron stars in this corner, that basically takes all the other stars and shoves them up into this corner. Like, a neutron star is so low luminosity and so hot that you could put the neutron star on the HR diagram, but then you wouldn't see any of the other stars because they'd all be crammed up in this upper right corner. So you just say, not worth it, right? And then where are the black holes? Well, black holes they give off no light, right? A black hole doesn't give off light, so it's essentially zero luminosity, and very, 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 very hot. So again, a star that's, a black hole is super hot, but also gives off no light, so it would be over here on an HR diagram. You don't plot them. It's just not worth it. What event happens when a high mass star dies? That's your supernova, right? The supernova explodes, and then the star goes from a red supergiant to off the board, off the HR diagram. There you go. That's how stars die, right? Once the star runs out of hydrogen, it doesn't die immediately. It kind of fights for its life for a while, right? A main sequence star is a main sequence star as long as it's got hydrogen in the core to burn. And once all the hydrogen runs out, then the star kind of fights for its life, trying to find another power source. It shrinks down, it burns helium, and then it shrinks down some more. And if it's a high mass star, it'll burn helium into carbon, and carbon into oxygen, and oxygen into neon, and et cetera, et cetera, et cetera. But again, even a supergiant is basically a star fighting for its life, trying to make some radiation pressure, trying to fight gravity, until eventually gravity wins. And when gravity wins, that's when the whole thing blows away. And that's the end of the story. And what you're left with, after all is said and done, what you're left with is the three ways that the three things that are left over when a star dies. Either a white dwarf, if it's a low mass star, or a neutron star if it's high mass, or a black hole if it's very, very high mass. All three of those types of objects, neutron stars, white dwarfs, neutron stars, and black holes, those are basically the skeletons left over when a star dies. They're all that's left. Well, they're all that's left, and all the gas that got blown out, right? Because most of the mass of that star got blown away as, got exploded out in the supernova, or a lot of the mass of this low mass star got blown away as the planetary nebula, and that's also what's left over, right? The mass that isn't trapped in the core as the white dwarf, neutron star, or black hole, that's also what's left. The gas that got blown out of the planetary nebula, or the gas that got blown out of the supernova, that gas is not trapped. It gets blown out so that gas can get mixed into the rest of the gas of the galaxy. And if that gas that got blown out of the supernova gets remixed into a molecular cloud, then that gas can get reborn into the next generation of stars. So the end of a star's life is not the end of the story, because the gas that gets expelled in a planetary nebula or a supernova, that gas can get recollapsed as it can get recollapsed as a molecular cloud, and it can get born into the next generation. The mass of the white dwarf or the neutron star or the black hole, that's trapped. That's not going anywhere. But the outer envelope of the star, that mass survives to be turned back into stars later on. Okay. All right. So, if that's making some sense, then we're ready to go on to the next step, which is, what about this life cycle? What about the life, the death, and the next life of stars? And what can we learn from that? So, okay, on to the next thing, and I'll see you there.